So it's highlighting pixels that are returned to the user that are relevant for classification. And so the weak point of these explanation methods or post hoc explanations is the lack of evaluation of the explanations generated by the model. So you have the saliency map here. You don't really know if is that the sort of the exact reason as to why the black box model has predicted an H. Well, we don't really know, and we felt that the evaluation of these post hoc explanations was poor. And so these explanation methods, what we want to answer in this thesis is how do these explanation methods perform when there's a ground truth explanation? And in this case, how do they perform when there's one and only one ground truth explanation to choose from? So we also answer how do these current state-of-the-art explanation methods perform when there are multiple ground truth explanations to choose from? And so we also answer, can these ground truth explanations be used during training to improve the quality of post hoc explanations? And then we also want to propose a new explanation method that outperforms the current state of the art. So we quickly discuss some related work here. So knowledge graphs store facts as triples and form subject, predicate, object. So you have a subject and object which represents some real world entity, and they're linked by some predicate. And so these knowledge graphs are often incomplete, and that creating the task of link prediction to identify unknown facts from existing ones. So in particular, graph neural networks can be used to perform link prediction on knowledge graphs. And so one adaptation of the graph neural network for knowledge graphs is a relational graph convolutional network, which we know in RGCN for the rest of the presentation. And this will just learn a d-dimensional vector for each node and relation in the graph. And so this will take as input an adjacency matrix and some given input triple. And it will output the probability that the given input triple is a fact. And so there's several algorithms have been developed to explain the predictions of these RGCNs. So the first one being explainy, which is for some node pair ij and a candidate explanation pair kl. Explainy will just simply compute the gradient of the scoring function for pair ij with respect to the adjacency matrix at kl. So in this case, the scoring function would be the RGCN. And then there is also GNN explainer, which learns a mask of the adjacency matrix to identify a relevant subgraph. And this is done by minimizing the cross entropy between the prediction made using the full adjacency matrix and a prediction made using the masked adjacency matrix. And so both of these explanation methods return an explanation in the form of a subgraph to the user. In this case, on a knowledge graph, the subgraph could be sets of triples. So we also use several different types of neural networks during this thesis. So the first one being a prototype network. And this is a specific type of neural network that returns explanations to the users in the form of a prototype vector. And this is a typical, what you call a typical observation from the training data. And these prototype vectors are serve as explanations based on the relative distance to the nearest prototype vector. So it has 4 loss function terms. So the first being just the cross entropy for the labels, which you can see, here. It also has an autoencoder, which reconstructs the input data here. So this is the loss function term for that. Then there are 2 reconstruction terms, 2 terms to penalize prototype vectors that are to be as close as possible to one of the encoded input training points. Then there's another term to encode every training point to be as close as possible to one possible prototype vector. So we also use LSTMs, and these are neural networks adapted to sequential data. And so this just uses gates to preserve information across time steps. And so it outputs a self state and a hidden state. And sort of the key idea is that it shares a weight matrix across time steps to preserve memory. So we also use a sequence-to-sequence model at some point in the thesis. And this uses an encoder-decoder framework. So you typically have two LSTMs, which you have here and here. This for tasks such as machine translation, and this computes a conditional probability of a sequence given some input. So here we have English to French translation. So we have cat is black and the chat est noir. So this is the input sentence, and then the model is asked to reconstruct a French translation of the sentence. So this can be adapted at some point to generate RGCN explanations. So we'll give an example here of why graph truth explanations are important. So we'll start by just building upon the prototype network we saw earlier. So these current methods use encoded inputs as features downstream, and so we felt that this could contain relevant information as to why the model is making the decision. And so we thought our idea was to perturb this encoded information, which could give us relevant input space explanations. So we have the prototype architecture here. And so we start by just encoding some trading points into the latent space here. And then we apply just M, which is just a mask over the encoded input. So that's just going to randomly set some of the values to 0. And then we decode this these masked values, and that is going to be reconstructed back into the input space using the decoder of the autoencoder. And so we just compute the difference between the absolute difference between the masked and unmasked points to give us relevant input space explanations. So we run some experiments on this proposed approach on the MNIST and California housing data sets. So the California housing is the tabular data. It has features such as longitude, latitude, number of rooms per household, neighborhood size, etc. And you want to predict the mean housing value. MNIST, as you may know, it's handwritten digits between 0 and 9. So we compare our results on both of these data sets with the state-of-the-art method for post-hoc explanations. And then we perform some sanity checks on the MNIST data set. And so there's some work showing that the saliency maps for image data can produce relevant saliency maps when the model's parameters are completely random, and also when the model is trained on random labels. So we perform both of those tests on this approach. So we also find high accuracy on both of these data sets of the prototype network. So we have our experiment here. We have the input images on the top here, and then we have some saliency maps generated from the proposed approach, and we can see that the saliency maps outline the image quite well. And then we perform using the proposed approach on a model where the model parameters are completely random. We can see that we would say that it passes the model randomization test because we can't really make out anything from this image. So we also run the proposed approach on randomly shuffled labels. So, and then we see that the saliency maps are different, but we can also see that even when the labels are random, we can still make out the pixels from the image. So we would say that it failed that test. And then this is these are selected examples of the California housing data set. This is 2 examples from line and then 2 examples from our proposed approach. And these are feature attribution scores. So a high value means that the post-hoc explainer has identified that feature as being the most important for predictions. And we can see what we can take away from these is that the top 3 features are the same for both examples. So sort of the reason for this this experiment was, well, we saw that the saliency map from this approach don't pass all of the sanity checks, and that in some sense evaluating explanations by comparing a small number of examples can be somewhat misleading. And we felt that this is a common problem in this field, is that explanations are evaluated only on a small number of sort of cherry-picked examples relative to some state-of-the-art algorithm like line. And that there's not really a thorough evaluation or scoring metric that's thoroughly defined and used across different papers. So also we noticed that it's difficult to determine when to prefer one explanation method over the other without some sort of standard framework. And it is the case where some of these post hoc explanation methods don't always return the same explanation to users. And so these problems could be solved with ground truth explanations, but this can be kind of non-trivial for some tasks and some different types of data. Also to note that there could be more than one way to explain an observation. And so data sets with ground truth explanations must include all of these possible ways to explain each observation. Otherwise, it could failing to do so would be unfairly punishing an explanation method that has identified some correct ground truth explanation that was somehow left out of the data. So in the section, we showed that our proposed approach didn't always generate these faithful explanations. It looked good on tabular data relative to line, but it failed the sanity checks on the image data, showing that it did not really didn't truly show what the model was learning. And we saw that these cherry-picked examples can be somewhat misleading, and that there should be research devoted to defining these ground truth explanations. Although we recognize this is difficult depending on the task and type of data, but we felt the scoring framework or evaluation framework should be defined before these algorithms to generate explanations are defined. So that one question would be, how do these explanation methods perform when they have actually have a ground truth explanation and they have a general scoring metric? So we'll do that for RGCNs using knowledge graphs. And so for explaining a gene explainer, neither of these papers use the same data sets or evaluation framework. So it's quite difficult to determine kind of which one is performing better or how do we compare these two approaches. So we have a proposed solution, and that's to use infer traces as an explanation. So we start by using an open source semantic reasoner chorus to build data sets with explanations using rules. So for an example of a rule could be for grandparent, it could be parent of my parent, and chorus would generate triples whenever it identifies two parent triples in that format. And so this will pinpoint all triples that have the generation of a triple. And so we have some example here on the graph. So we have two triples in the graph. Princess Marianne has parent Louis XIV. Louis XIV has parent Anne of Austria. And so chorus will identify a new triple. It's recognized the pattern of has parent, so it will generate a new triple. Princess Marianne has grandparent Anne of Austria. And so this would serve as, in our data set with ground truth explanations, we would have our input triple with has grandparent, and this would be fed into explain your gene and explainer. And we would ask them to return these two triples as the explanation. So we define two data sets, the royalty 20K and royalty 30K, with these rules: has spouse, has successor, has predecessor, and then on the royalty 30K is has spouse and has grandparent. And these rules are defined such that there is one and only way to explain each triple. So these are this is a table of data sets statistics. We have the royalty 20K and 30K. Then we have the different predicates that exist in the data set, the number of triples, number of rule generated triples, number of unique entities or nodes, explanation cardinality, which is the number of triples needed to explain that rule. So for example, has spouse just required one triple, whereas you saw with has grandparent required two has parent triples. And then lastly, we have the predicate property, which is for spouse, it's symmetric. So these the subject and object are just switched. Inverse means that successor and predecessor explain each other. And then grandparent is the chain where it's has parent. So we're going to benchmark on these two data sets of these RGCN post-hoc explainers. And we use the royalty data sets to compare these two. So we propose the use of the Jacquard similarity between the predicted and ground truth explanations. but we also report the precision recall and an F1 score. So these are explanation evaluation results on the two data sets. So we have the full data set on the far right, and then each one of these columns represents a subset of the data only using that predicate. So these are this is a data set only using has spouse, only using has successor, has grandparent, etc. So we can see that explaining for the Jacquard similarity, explaining significantly outperforms the GNN explainer. And we also perform an error analysis. So the first thing we evaluated would be the most frequently predicted predicate. So this table just essentially shows for some data set that were 20K on has successor predicate. You can see that it's 78% of explaining errors contained has successor, whereas for GNN explainer, 50% of the errors contain has predecessor. So what we can take away from this table is that the types of errors that these models make are not the same. So we also, for explaining, we report the most frequently missing predicate. So this is just saying that for the royalty 20K and has successor, has predecessor is missing from 78% of the errors. We define an error to be any prediction where the Jacquard score is less than 1. So you can potentially partially predict a correct explanation. If you had on has grandparent, for example, you could have you could predict one of the parents correctly and the other one incorrectly, and so that would still be considered an error. And so these are just histogram counts of the most frequently predicted predicate across both data sets for every subset, and then this is the top being explaining and the bottom being GNN explainer. And so what we can take away from this is that we can see that GNN explainer makes some more uniform errors, whereas explaining is consistently predicting the input predicate. So in this section, we showed that pinpointing can be used to generate these ground truth explanations, and that both GNN explainer and explainer lack a common data set and evaluation metric. And so we proposed these two data sets with the use of the Jacquard score, and we showed that the explaining outperformed the GNN explainer on these data sets and metric. So this doesn't address the case where there are multiple ways to explain an observation. And so, one question we would ask is, how do we know if there's multiple explanations? How do we know which one to choose from? And so we also address this issue of benchmarking explanations with multiple ground truth explanations. So we have an example here. We have two triples in the graph. Adele of Champagne has child Agnes of France, and Louis VII has spouse Adele of Champagne. So we can use rules to define new triple. Louis VII has France has child Agnes of France. And so again, this would be the input triple fed into explainer, GNN explainer. And these two triples would be, we would ask explainer and GNN explainer to identify these two triples as the explanation. But as mentioned earlier, there could be actually more than one way to explain why Louis VII of France has child Agnes of France. Right? You could say Agnes of France has grandparent Louis VI, and Louis VII has parent Louis VI. So there's more than one way to explain why a link exists between these two nodes, but it's unclear which one of these explanations is optimal. So starting in this work, we perform a user experiment to determine which explanations are most intuitive. So we construct a small complete graph using all family relations. And we have enumerated all paths with a maximum length of 2. And each one of these paths serve as a possible explanation. And the user experiment, users are just asked to identify which explanation is most relevant, and then we use these scores as relevance weights. And they're given, each explanation is on the Likert scale between 0 and 4. 4 being the most intuitive, 0 being not intuitive at all. So this, we construct our French royalty 200K to benchmark these methods on multiple explanations. And then this uses 6 relations. So it uses has brother, has sister, has child, has parent, has spouse, and has grandparent. And for every triple in the training and test set is included all possible explanations as to why a link exists between these 2 nodes. So this is a breakdown of the data set. So we have the first column is the predicate, the number of triples. This is the explanations. So, for example, you could explain why A has brother B because, well, they're sisters, or they have the same parents, or they have the same grandparents, etc. And then the next column is the user score. This is these are the scores that the users determined to be the most relevant explanations. So for has brother, the users decided that 2 people with the same parents is the most intuitive explanation. And then lastly, we have the explanation type. So this just determines, well, there's 2 types of explanations, logical and partial. So a logical explanation is one that's true every time, and a partial explanation is one that's only true if you have additional information. For example, if I told you 2 people had the same parents, you wouldn't know if they're brother or sister unless you knew their gender. So we distinguish these 2 between logical and partial. So we also propose some performance metrics for non-unique explanations. So the binary precision and recall fail to account for the fact that some of these explanations can be more intuitive than others. And so we adapt the generalized precision and recall to account for the relevance weights as determined by the users in the experiment. So starting with the generalized precision, we have EI hat is going to be that's the triples in the predicted explanation, and then we have EI is the triples in the ground truth explanation. We take the intersection of the cardinality of the intersection and multiply that by the user score of the ground truth explanation. And that's going to be normalized by the number of triples in the predicted explanation, and also by the maximum user score. So also similarly, we have the generalized recall where the numerator is exactly the same. And then we normalize by the number of triples in the ground truth explanation. And so this is normalized by both of these are normalized by the max user score to keep the value between 0 and 1. So we also compute the Jacquard score for every possible explanation. And then we report the maximum Jacquard across each one of those explanations to show the very best performance that the models could do. So again, we run another benchmark of explaining a GNN explainer on this French royalty 200K. So these are the results. So the top section here has the full data set, and then these are each subsets of the data. So for has spouse, this is the results when it's only trained on has spouse predicates, has brother, etc. So we can see that explaining outperforms GNN explainer across all of these metrics for all subsets of the data. And then we additionally break down the full data set in this section below. And this is just filtering the has spouse results, has brother, has results, has sister, etc. of the full data set. And this is the distribution of user scores amongst errors. So this is just for each of the user scores. We wanted to see where the errors were coming from, which user score the model attempted to predict. And so we say, explaining on has grandparents made 850 errors on explanations with a user score of 0.7. So kind of what we can take away from this is that these models aren't attempting to predict the best explanations, rather they're predicting the explanations that have a score of 0.7, and that's because the majority of explanations have a user score of 0.7. So we showed in this section that there could be multiple ways to explain why an observation, and that there's no data set of scoring metrics that exists for multiple explanations. So we proposed a data set and define several scoring metrics, and we run a benchmark, and we find that explaining outperforms GNN explainer on this data set of metrics. And so one question that leads into this is, how can these ground truth explanations be used in training? And how will that impact the GNN explainer and explaining performance when we make changes to the embedding? So in this section, we discuss just that, the impact of injecting ground truth explanations into the RGCN embeddings. So as you saw, the explanation methods were shown to produce errors. So one question that stems from that is, where does this, when an error occurs, where does it come from? Is it from the graph embeddings? Maybe they're undertrained, or maybe they're poorly trained, or is there just some inherent flaw with explaining a GNN explainer? So our proposed solution is to further constrain the loss function of these RGCNs and then incorporate this prior knowledge of the ground truth explanations into the embeddings. And so we use the ground truth explanations during training, and we want to see kind of how these performance metrics that we previously defined change when they have access to more information. So we further constrain the cross-entropy loss used by the RGCN, and that'll be shown here. So this is just a standard binary cross-entropy, and then we sum across the set of all positive and negative triples. And this is going to be normalized by the number of unique entities and the number of negative triples. And so we'll add constraints to this in the following slides. So starting with, we start by penalizing the cross-entropy term that you just saw with this L2 distance here. So this is just a penalty term that pushes the subject and objects, the embeddings of the input triple towards the subject and object embeddings of the explanations. So we take the maximum of the embedding from this is the subject of the ground truth, between the distance of the subject and the explanation. And we compute the maximum of that with the subject of the explanation and the subject of the input triple and the object of the embedding. And so we also do that kind of the inverse for the object as well. So we have TP, which is an input triple, and then TJ, which is an explanation triple. And so kind of a motivating example for that is, if you had some input triple, John has parent Tom, and Tom has child John. Well, computing that L2 distance, this is just, we have the subject here, and then we have Tom, the object. This is just an L2 distance. It's going to be 2 times the L2 distance between these two. However, if you change the explanation triple to John is child of Tom, well, then this leads to just an L2 distance of 0. So we wanted to include both of those terms in the maximum because the information is the same, but the penalty term is different in both of these cases. So we wanted to include both of these to account for this ambiguity. So we will take the cross-entropy term from the RGCN, and we'll add that L2 distance that you saw in the previous slides, and this will just be summed across every explanation. So we have the set of positive triples, and then we have an explanation which contains at most 2 triples. The royalty 20K and 30K, where there's only one available explanation. But for the French royalty 200K, we have an additional summation term here because we have to sum over all possible triples available to the model. And then again, we have we sum across the particular explanation and all the triples that exist in that explanation. So we also try another loss function, and we compare the results of several of these loss functions. So this one is essentially just scaling the L2 distance by the user score of the explanation. So this is the relevant score. It's multiplied by the distance. And this is very similar to the previous equations, but this is solely focusing on the relevant score of each explanation. And so this term was developed because we wanted large distances of the relative explanation to be penalized more than distances of irrelevant explanations. So lastly, we have what we denote Lmax, and this is just going to take the highest available user score and apply that L2 distance to that triple or that explanation. So this is the explanation with the highest relevance score, and we compute the L2 distance. That's denoted Lmax, and this is similar idea. It's going to push the subject an object far away. So there's an object of the best available explanation as determined by the relevance scores. And there's multiple explanations available. We take the explanation with the best score, and the embeddings from the non-relevant explanations are not considered. So again, we've run another benchmark of explaining a GNN explainer using these different loss functions and seeing how the explanations change. So we use the royalty 20K, 30K, and the French royalty, and we report the Jacquard F1 and recall and precision for the royalty 20K and 30K. Then we report the max Jacquard generalized precision and generalized recall and F1 score for the French royalty 200K. So these are explanation evaluation results. So the top row has for the French royalty 20K and 30K, it has the link prediction accuracy of the baseline RGCN, and this is the penalized RGCN. We can see that the link prediction accuracy suffers a little bit relative to the baseline when it's further constrained with these explanation embeddings. We can also see that the explaining and GNN explainer are the baselines are both outperformed by this proposed approach. Although we can also see that the explaining performance is much higher than the difference between the baseline GNN and penalized GNN explainer. So we also report results on the French royalty 200K. And this is starting with the link prediction results. We got the baseline and 3 different methods. We find that the baseline actually outperforms the other models on the task of link prediction. But then for explanation evaluations, we find that the penalized approaches have a higher max Jacquard for GNN explainer. Although we can see that the results are very, very close. And then on the results for explaining, we can see that the results are much higher. So we perform an error analysis on these 3 different models. So this is, again, the most frequently predicted predicate. So we can see that explaining with the L-sum penalty, the most frequently predicted predicate is has predecessor, whereas for GNN explainer with the penalized loss function, 52% of the errors contain the has successor predicate. So again, we can take away from this table is that the different models make different types of errors, right? So this is the most frequently missing predicate. So the penalized explainee uses the RGCN with L-sum and the explainee on the royalty 20K, but it has successor subset. Only 6% of errors contain has predecessor predicate, and for GNN explainer, it's 52% of the errors. We're missing the has predecessor. So we also report a histogram of the most frequently predicted predicates amongst errors. So this is the royalty 20K, the royalty 30K, and then we have the French royalty here. We can again take away from that these 2 models make different types of errors and different types of predicates show up in the error. And this is the distribution of user scores amongst errors. So this is, we have GNN explainer on the left and we have explaining on the right. So you could say that the GNN with the penalized RGCN made 214 errors on the has-spouse subset. And those errors had an explanation, the user score of 0.8. So we can also take away from this is that even with the penalized embeddings on the RGCN, these explanation methods still make the most errors on the explanations with a score of 0.7, rather than, although ideally they should be making mistakes on 0.9, but they're not. We can see that they're not attempting to make a prediction based on the user score, but rather it's just the majority score. So in this section, we showed that there's multiple ways to include prior knowledge into the RGCN embeddings, and that we perform a benchmark of these GNN explainer and explainee, and we see that explainee outperforms GNN explainer again. But we also noticed that explainee's performance metric changed more so than the GNN explainer. And we also perform an error analysis to show that these models make different types of errors. So that leads to a kind of a natural question is, can we create an explanation method that produces competitive performance? So we'll do that using sequence-to-sequence models, as we discussed earlier. So we saw that on the other data sets, explainee and GNN explainer had low performance in terms of recovering these, generating these explanations. In particular, we saw that performance was low on predicates where there were multiple triples in the ground truth. So, for example, we saw low performance on the has grandparent subset where there's 2 triples required to correctly predict the explanation. In both of these algorithms have in common is that they operate on the adjacency matrix. So GNN explainer has a parameter for each element in the adjacency matrix, and explainee computes a gradient for each element of the adjacency matrix. So we wanted to propose a sequence-to-sequence model that has a competitive performance, but also has a smaller number of parameters. So we also propose an approach to generate false triples, which helps train the sequence-to-sequence model. And we also perform sanity checks to determine model robustness, as we saw in the early example, the motivating the need for ground truth explanations. So this is a sequence-to-sequence model that's trained on input to triple explanation pairs. So we have as an input here, it's no longer a sentence for machine translation, but rather this is an RDF triple. So this is Louis VII has spouse Adele of Champagne, and that's is inputted into the model. And so the model is asked to, well, the model is going to be fed the explanation of the input triple. So we ask this, it uses an encoder decoder, and we ask the decoder to output in the first time step a true or false token, and that's to determine whether this input triple is true or false. Then the resulting steps in the sequence are the explanation serving for the input. And so this will be used to generate RGCN predictions, and kind of the motivating idea for this is that we saw the performance was low on the has grandparent triples, and we felt sequence-to-sequence model was a good idea because it can generate sequences of arbitrary length. So we also propose the use of false triples to help training. So the royalty 30 decay, as you recall, uses the has parent, has spouse, and has grandparent triples. And so we propose that for every has spouse triple in the data set, we construct a new false triple has parent. And this is because spouses cannot be the parent of one another, and well, but none existed in the data set. So when we have a false triple, Louis VII has parent, Adele of Champagne, this is false. So this is going to be when a false triple is identified, it will output a false token in the first time step, and it will terminate the sequence. So these are the explanation evaluation results on the French royalty 30K. So we have the sequence-to-sequence model with counterexamples. Without counterexamples, we can see that there's a significant performance jump on the full data set, but also we can see that on has grandparent, there's a significant increase in explanation quality. So we've also proposed the use of 2 sanity checks to verify model robustness. These are inspired by the previous sanity checks from the sanity maps. So these are we shuffle the explanations. So the sequence-to-sequence model is trained on on a data set where the ground truth explanations are randomly assigned. And then we do the random embeddings where the sequence model is trained on the RGCN embeddings that are completely random. So of course we shouldn't expect to see any meaningful sequences generating on these during these two sanity checks, and we see that the results is that we would say the model passed both of these tests because none of the sequences were meaningful in any way. So wrapping up with conclusions and future perspectives. So in this thesis, we benchmark explanation methods on unique ground truth and proposed appropriate scoring metrics. We also benchmark explanation methods for the case of multiple or non-unique explanations, and we proposed some of scoring metrics. And then we incorporated this prior knowledge into the RGCN embeddings during training, and we proposed the use of a sequence-to-sequence model for the RGCN explanation generation. So some possible extensions of this thesis, kind of going back to this idea of the prior knowledge into the embeddings. When an explanation method produces some incorrect explanation, where does this error come from? Is it the bad embeddings, or is it just some flaw with the post-hoc explainer? This is something that is still open research. Additionally, even if one way to answer this question of if the embeddings are bad, we would sort of need a way to identify what information is captured in the graph embedding. We want to ensure that the embeddings have captured the relationship between the input triples and the associated ground truth explanations, but we would need a method to do that. So also with the sequence model has some limitations. So we found that we had to pre-train the RGCN and freeze the embeddings, and then train the sequence model after. So one idea could be to modify the architecture to train the RGCN and the sequence model kind of in an end-to-end fashion at the same time. So we also performed experiments only on the royalty 30K data set for the sequence model, but we wanted to adapt that at some point to the case of multiple explanations and train on the French royalty 200K. Also, you saw we proposed an approach for counterexamples. Although ideally, we would like to propose an approach where counterexamples are not needed at all to maintain this competitive performance. And lastly, we would like to adapt this approach such that it doesn't use ground truth explanations in training at all. So this means kind of developing an unsupervised approach where the decoder does not see the ground truth explanations. And this would create some sort of generalized black box explainer that produce faithful explanations. I think that's it.